talk on automatic inference of relational object invariants, and it's presented by Arie.
Well, this is, I think, the toughest presentation for me because I have to stand here. This thing is right in my eye, so I don't see any of you. And apparently I can't move, but let's see. So this is joint work with Yusen, Jorge, me, and Isabel. Unfortunately, I am presenting. Yusen did the work. He should present, but this probably by now we're noticing there's so many problems with visas in the US. We had a conference in Canada last year. Lots of people can come. It's just getting worse and worse. But you got me instead of him because of visas. So what I'm going to talk about is automatic inference of relational object invariants. So let me set this in. It's a very simple problem. We're kind of surprised there wasn't a solution like this before. We're just putting it out there. So the goal that we want to do is we want to do abstract interpretation, static analysis by abstract interpretation. We want to automatically infer properties of memory objects. So think like a buffer that has length and capacity, and you want to know length is always bounded by capacity. Capacity is always greater than allocated space. This kind of relationships. We want to analyze C code, but really not C code, but rather how it's compiled into LLVM. So we don't want to depend on some syntactic similarities of C. Sometimes in C, you have something that's sort of very clear and simple, one line, ends up being a lot of generated LLVM code. So we want to be at this low level. And the challenge is that if you try to do this, if you just apply normal analysis that you have, you're going to discover that the way things usually are defined, anything that's in memory gets weak updates. And so you lose any of the relational properties. So I'm going to do a little bit of setup to explain this to you, why this happens. And then hopefully our approach will be very clear. So we're going to play with this program. This is a made-up program, but it's a sort of a good illustration that fits on one slide. What happens in the program, there's two parts. There's a loop and something that happens after the loop. Inside the loop, we allocate a whole bunch of resizable buffers. A resizable buffer in C will be two objects. One is a whole data. This is allocated at the bottom. We're not going to do much with it. It just has data. And the other one is a header. The header is a descriptor of a buffer. Will tell you where the data is. It has a field called the buff that points to data. It's going to have a field that tells you how much space the buffer has. That's capacity. And it's going to have a field that tells you how much of it is already used right now. That's the length. Right? You've all used vectors. You've maybe implemented things like that in like second year computer science. You should all understand how this works. You allocate a bunch of memory. Capacity tells you how much. Every time you add something, you increase length. Eventually, you reallocate. Here we have buffers of different size. They're being allocated, stored in some array, they're actually of different size, but always length is less than capacity. Then later, we allocate a new buffer, and we modify something and stick it back into the same array. And what we really want to know is we want to prove that length is always less than capacity. Therefore, all the memory operations here and elsewhere are safe. Now, the first problem that we face here, in this case, is that we're going to have a lot of abstract objects because lots of things are allocated. That's a challenge. Our abstract domain will start exploding. We want to compress it somehow. And the typical solution that I think almost everybody does is something called allocation site abstraction. You basically say all objects that are allocated in one program location and one allocation site, they become one abstract object. And they all share their properties, and they're represented as a summary object. You can play with this a bit. There's lots of directions where you can say whether it's really an allocation site abstraction, or you refine it further, where you say actually depends on some other extra context, or you merge multiple allocation sites together because ALS. But at the end of the day, you break the program into finitely many abstract sites, and each abstract site gets an abstract object. You apply this to this problem, and then you're going to have one summary object that tells you about all this buffer that you allocated. Now, when you do this, and you try to run your analysis with this program, what you're going to discover is that, interestingly, the final invariant you want is representable, length less than capacity for all of the summary objects. But this invariant is broken temporarily when the program runs, especially if you look at the low-level operations, and restored only when the object is completely filled. So if you try to run it here, you'll see that actually after an analysis, no matter how precise your abstract domain is, you're not going to get length less than capacity because somewhere in the middle, you're going to be updating length of a new object, but not yet the capacity of the new object. And now it's in a summary object. You have some objects which are in a bad state, some object in a good state. You get top as the abstract value, or maybe some bounds, and that's it. That is a problem we want to solve. Now, if you worked in this space, and if you've seen this before, then you immediately will tell me, yeah, but this problem is solved. There is a thing called recency abstraction. It's exactly your example. Okay? And if we go back at the example, this is actually what's done in abstract interpretation, also what's done in like almost every modern compiler. You do a little trick. If you look inside the loop, it's very clear that what is being accessed is just the last malloc. So you can single out this last malloc from the summary. And you say, until the address from the last malloc escaped somehow, I know that I'm updating this one specific object, the last malloc object. And then only when I'm done with this, I'm going to stick it back into memory. This is an abstract interpretation known as recency abstraction, where you separate your abstract objects in addition to which allocation site, whether it's the least allocated object or whether it is another object. Okay. So that solves this problem, the first loop. But of course, it creates another problem, or doesn't solve the problem. That's why we have stuff after the loop. Recency abstraction only works for the first allocated object. But often our code is not just creates objects when they're allocated. The code will often pull a buffer out of memory. The buffer has its invariants. It will modify stuff in a buffer. The buffer loses its invariant and eventually regains it. And then this buffer is stuck back into memory. And recency abstraction will not help with this. So this, okay, so this is an example of the recency abstraction. And so then this immediately sort of gives out our solution. So we want to update the recency abstraction to, instead of keep track of most recently allocated object, the most recently used object. So we're going to have the most recent, it's called the recency use abstraction. And so the rest of the talk is just to tell you, so you start with this idea, it seems very obvious. What are the challenges that you need to solve in order to get to the final solution? And how do we put all of this together? And of course, there's going to be experimental results, because that's the only way we know that it works. And so obviously, you'll see it works great. Now, I'm going to confuse you a bit. Maybe not. But in order to prevent confusion, I'm going to first talk about methodology so that you don't get confused. How do you define a new abstract domain, a new abstract interpretation? Well, one way is you can define a very fancy abstract domain, show how all of the operations are done and that they're sound, and you don't. But this sometimes is very hard if your concrete semantics is missing some important concept that you would want to have in your abstract semantics. If you still just go and design an abstract domain just as is, you're going to run into a big problem that your abstract domain will be very complicated. But really, just because you're trying to capture something in the declarative way of the domain from the semantics. So we're going to go a different way. The way we're going to go is we're going to give you a completely different concrete semantics. This is where the confusion may happen. I'm going to talk about the concrete semantics, and you may have two questions. One, well, how do I know this answer abstractly? And you won't until I get to the abstract domain. That's concrete semantics. And the second one is how you're going to convince anybody to build this architecture. It's stupid. I'm not going to convince anybody to build this architecture. This is just how I'm thinking. Okay? Another way to do it, if you want to do it more principled, you build the series of abstractions. You sort of start with your concrete semantics, you build an abstraction into the semantics you want, and then you build the abstraction for the analysis. But we're doing it sort of in a more concrete, hands-on way. We're just building a new architecture. Now, what do we want from this new architecture? We want to be able to say, to connect the concept, most recently used memory object, which is a very abstract concept if you want to think about it in terms of sort of a C memory model, what an object really is, to something very concrete, so that I don't have to just dance around you telling you, this is what most recently is and this is what isn't. I just want to have a thing in my memory model that I can point to. And so the way we were thinking about it is that it would be easy for us to do this if we think of a memory model with a cache. So imagine that instead of a normal memory model where you just grab a thing that you want, I give you a cache. Now, you have to compile your program to use this cache effectively. That's going to be left out from here. That's, if you compile it ineffectively, it's still sound, you just don't get the benefit. So what do you need to do? Whenever you have to access main memory, you're no longer allowed to do it. You have to bring memory into the cache. How much memory do you bring? Well, you have to bring an object into the cache. So if you want to access, say, address 500, you can't access address 500. You have to bring an object to which address 500 belongs. How do you know which object that belongs? It's up to you. Compile efficiently. You want to compile very inefficiently, you say my cache is just my whole memory. All objects belong to just this one memory object. I just bring everything in. And then you basically get one summary. What we actually do once we get to an implementation is we have an analysis based on LS analysis that breaks memory into LS sets. And each LS set gets its own memory cache. So it depends on how fancy your compiler is. We're just talking about once you do it, what the meaning is. So what do we have here? We have a memory is divided into memory banks, so that whenever you allocate memory, you pick which bank. Ideally, you would want to have each allocation site has its own memory bank. Each memory bank has a cache. Every time you want to access memory, you go and load it into the cache. The cache, in addition, has a whole bunch of logs that tell you, what state is it in, is it used, not used, and so on. This is our concrete domain. It's a product of domains. We have scalars for registers and things like that. Memory, which is a product because of memory banks. And then each memory has the storage, which is just a blob of memory, a cache, which is basically one memory object, and a bunch of logs. And so in order to sort of give you a hint of how this works, I'm just going to quickly animate through an example of executing the program under this memory model. And again, remember, this is all concrete. So I know exactly which address I'm using. I'm not worrying about LSing and all of those things. It's just the memory model. So I'm in the beginning of a program. I set I to 0. Only the scalars changed. I come to allocate memory. I got a new address. In my storage, I now know this address is allocated. There's nothing in the cache. I come to assign plan I. Now, it looks like it's just one line, plan I. In low-level LLVM, it's actually a bunch of lines. I first have to get the address of P. Then I have to add the offset of len, in which case 0, which is a new address, a new variable now called plan. And then this variable, I'm going to have to store I into it. So I'm doing all of this. And then what happens is that I'm going to do this update. I know that the cache is currently empty, it has nothing in it. So I now allocate the object at address 1000 into the cache, and I write my value into the cache. So you see here, where is it? Here at the bottom, the 0 is written into the cache, not yet into the storage. And then it continues. I'm executing, things change. I is incremented at the bottom. None of this affects the cache. The object is still in the cache because we know that the last object we used was an address 1000. The cache remembers this. Nobody written to memory yet. It just stayed there. We allocate the second object. We now have the second object. We haven't used the cache. At some point, we start doing a memory operation. We now know that we need to bring 2000 from memory into the cache, which means we have to flush the cache first. To flush the cache, we go through the steps. So this is sort of the semantic step that we want. And this is the micro-architectural step that we want. Right? We want a new object in a cache, new value updated. But in order to do this, we first flush the cache into memory. We then re-update the cache based on the new object. Then we write the value in there. So, and once we get to the end, once we get to the last iteration, same thing. We have something in the cache. We're about to access a new object. We load the new object in the cache and we access it. I mean, hopefully by now it's all clear. The only question is like, why would somebody build this architecture? So we don't want to build this architecture. What this architecture gives us, it gives us all of the necessary mechanisms in order to layer our abstraction. So we can show, and it's quite sort of obvious, that this memory model is compatible with the C memory model. I can easily write a compiler that will compile towards this memory model. And if a program is sound for C memory model, it will have the same behavior on this one. I can have a fancy compiler where I have lots of different memory banks and I try to optimize this. And I can have a less efficient compiler. That's up to me. So now if we want to build our abstraction, so we get to the abstract domain. All we have to do, all I have to explain to you, is to explain how we layer the different domains. Okay. So now we know what the most recently used one, that's a cache. I need to have enough knowledge to know when to flush the cache. And I need to somehow propagate information across all of those different pieces. So this is how my abstract domain looks like. Again, it's going to be a product, modeling sort of what we have concretely. There's going to be an abstract domain over cache. We really want to think about it as some kind of relational domain like octagons. Otherwise, this is less useful. There's some domain for summary, probably the same as for the cache. We're going to move from summary to cache and back. There's domain for flags. They're Boolean, so we can represent them more or less precisely. There's domain for scalars, which is registers. Again, we have some fancy domain for this, probably also octagons, maybe even fancier. And then the important part is we need to keep track of all of those memory addresses to know which one is loaded where. And we don't want to put a lot of effort into it because we don't have any specific allocator. So if I tell you that a memory address is in some range, well, that really doesn't mean anything because it all depends on how allocator does it. And so we're going to add a whole bunch of equality domains to keep track just of equalities. So what we really care about is whether the cache is being accessed by the same address or from the same base address as it was recently. If it wasn't, we flush. If our equality domain is imprecise, or the program is written in some strange way, where, for example, it gets one object from memory, updates one field, then gets another object in memory, updates another field, and keeps switching, as opposed to getting an object, ensuring that it satisfies its object invariance, and then moving to the next one. So in one case, we'll do badly, and if a program is written well, we'll do well. In both cases, will be sound. So the trick here is really picking out these domains and figuring out how to do all of the reductions. Because if you try to be very precise at every step, this is just too expensive for this model. So again, just like before, I'll run through an example. And I think I'm kind of low on time. So this is a very detailed example, really meant if you want to sit down with the slides, click on different things and see what changes. Hopefully understand where this is going, so I'll just run very quickly. Just kind of get to see which parts of which picture get to change. We start in the beginning. We don't have any equalities. We know that I is 0. We have nothing in the cache, no summary. We start to allocate an object. We have an address. Now we abstract. We don't know it's 1,000, but we know it's not 0. We assume that malloc doesn't fail. We then compute plen. We know that plen was obtained by pointer arithmetic from p. Therefore, their base addresses are the same. So that's the first equality we get. We then we know that len equals I, and we know that the object that we need to go into the cache is the same object as p base and plen, the one we accessing. And then, of course, eventually the result gets in the cache. That's a strong update. We only had one object. This is just like recency abstraction, but just slightly for different reasons. It's not because it's last allocated. It's because it's the last address that we knew that is being used in the cache. And then this continues. So as we go to the second object, again, before we started using memory, nothing changes in the cache. It just lives in the cache. Once we get to start using memory, we have to flush the cache. This is sort of modeling the same microarchitectural steps, but now abstractly. And you have to keep track of where the equalities flows. But mostly we just move the cache line into the summary line. And then we come back, and now we can use the second cache, and so on. At some point, we're going to come to a join. So this is a join of the loop. On one hand, we have one object allocated, and it's in a cache. On the other hand, we have two objects, one in a cache, one in main memory. We have to join. Of course, the different ways to do it, and the solution that we pick is we flush before every join. So we see that an object on the left is in the cache. We flush it into memory. Now we have, and the second object, we also have an object in the cache. We flush it also into memory. And then we join the two using the normal join. So what will happen here is that we do get to keep that length is less than capacity, but we do lose the fact that on one hand length is 1, and on the other hand the length is either 1 or 2, depending on which object you're in. So smoosh them together. And same will be with widening. When you have to do widening, the same thing. You flush into summary and just do normal widening. And OK, so this gives you the invariance. And then if we want to do a write after the loop, you can see what's going to happen. It's the same thing. We have this object invariant in the summary. We bring it in. We modify the loop, the element. We know that the object in the cache is the one we're accessing. We do strong updates. And then when we're done, we get to keep the property. Perfect. So let me stop here and see if there's any questions about what we do before I go into how amazing it is. OK, so I think there was a question behind you first. No, wait. There's a question there first.
A quick question. I'm in CPS. I'm completely not in the field, but I'm just curious, like, if you have different applications, will this be challenging? Because like your cache utility, right? You don't want to flush other applications' data into the
So remember how I said I will confuse you? I managed to succeed. Good for me.
No, because I'm not in the field. So
No, this is great. So the cache here is just a mechanism for me to be able to say, before the cache is flushed, I do some abstract step. So I introduce this notion of a cache so I can make this kind of statement. And then I say, well, whenever you compile your program into this architecture, of course, you should minimize the number of flushes. If you have a lot of flushes, it's going to be imprecise. You're going to lose precision. It's going to be inefficient. If you manage to compile a program with few flushes, it's going to be more precise. I'm leaving out how do you compile into that architecture. That's outside. All I'm claiming is that I can compile my programs into this architecture efficiently. Not telling you how, but trust me, and I give you my code. And I'm claiming that if you compile into this architecture in any way, my result is sound. Okay? So your point is when you look thinking about the cache is correct. Like, how do you do this efficient compilation? I'm leaving this out.
thank you so much.
Cool. So it sounds like the cache has exactly one object in it, right?
It can have more.
OK.
And
that's kind of my
course,
question.
The abstract domain for the addresses can be more refined. So we chose one. And I mean, I haven't shown you yet the empirical results. And you'll see it's not as rosy as you may think. And so having more objects will make it even harder. So that's sort of the thing. But conceptually, sure, you can have lots of them. And all you have to do is just manage your address domain has to be more advanced than just simple
knob
equalities.
you can control to have more precision, but more complex, right?
Well, for example, you may want to say I have two caches because I have objects actually from two different allocation sites, so different types. And I have one cache for buffers and one cache for something else. But then in my abstract domain, I need to be able to know if I have an address, what address is it? Because if it's always either one, then I'm not going to benefit from the refinement in caches.
Got it. Thanks.
You have a clarification comment?
Yeah. In the alias domains, is it must alias? Is it in the alias domains equality? Is it must alias or may alias or something else?
I don't understand may and must alias as terms. I don't know what they mean. The domain that we have is a domain of equality. And so either you know that the pointers that you're writing to equal the pointer, the object that the cache keeps.
Okay, so it's a must alias, in fact.
Okay.
Yeah.
But we don't compute it as an alias analysis. We just have an equality domain. Right? And so part of the abstract domain, that computation happens.
Maybe you should go to the results and then we'll come back to the question.
All right. So this has been implemented. This has been validated and repeated. It's amazing. Now, for experiments, since I'm running out of time, I'm going to try and summarize my problem with experiments rather than the experiments themselves. This kind of work is really hard to evaluate, at least for me. The difficulty is that well, we want to know if it works. So we can run scalability. Then we need large programs, but then we don't have properties for them. What do we know? We can say, let's do memory safety on a large program. You do memory safety on a large program, you're never going to succeed. You're never going to prove it completely safe. So now you can say, I prove 80% of the checks. But how do I know that those 80% are actually the hard ones? Maybe the 80% are easy, and there's like one that's hard, and whatever I do made no difference. On the other hand, I can do small programs, but then why do you need this kind of technique? Why won't you just lower everything to SMT and do it in that way? So we try to address this a bit by trying different ways to evaluate it. We have some evaluation that looks at scalability, which takes a previous technique that we also developed, takes a corpus of small programs, but large, they're like hundreds of thousand lines of code, and we show it scales how we expected, because we cut the abstract domain into small pieces rather than one big octagon. It scales how we expect. We have experiments for precision where we craft special programs that we know would be really good for our technique, shouldn't be handled by, say, recency abstraction and other tools. We compare it with MOPSA, and yeah, we get exactly what we expect theoretically, that this technique works well and recency abstraction doesn't. And then we embed it into a bigger pipeline. This is sort of what gave us reason to work on this in the first place. We have a case study where we're using bounded model checking to verify real AWS code. The code is small, but we verify complete memory safety of it. And we thought it would be cool to put an abstract interpretation pipeline up front and in the middle. Up front, because this is BMC, so it cuts loops. So up front is before you remove the loops. But then after you cut the loops, there's still a lot of reasoning that you can do with abstract interpretation before you go to SMT solving. So we also put this technique after the loops have been cut. And we compare how much effect it has on BMC. And here the results are very mixed. Again, there's a lot of details and numbers and things that you can look better in a paper. But the big problem is that if you start to work with BMC, you start finding SMT solvers that are not monotone. So for example, we can show we do pretty good at removing checks that an SMT solver doesn't have to do. This doesn't necessarily make SMT solver faster. Sometimes it makes it slower. And so we still work to do how to integrate this in such a way that it's always, always good. But it's definitely something that you want to have as part of a pipeline because it does give you benefits. So that's it.
So one question I had is, can you actually try to extend this to prove properties that are very hard with this materialization, summarization, recency abstraction? So for example, if I had a buffer where things later in the buffer, like in your resizable buffer, things later in the buffer are larger than things earlier, you might have to reason about two objects at the same time, right? Could you try things like that with now that you can materialize multiple objects in your cache?
Right, like this is the direction. Actually, when we started, we thought this will be easy. And then we'll do fancy things like multiple objects in a cache or separate, but this was hard. So it's conceptually easy. Then getting this idea, we can just change the concrete semantics. So it's very easy for us to think about it concretely and then what the abstraction means. That's easy. But getting this to work, the part that I skipped is fine-tuning all of the reductions so that you're actually still effective. That was hard. But yeah, like this is, and I think thinking in terms of this architecture that we can just add more things like caches and various things, and then we abstract them separately, that's maybe a good way to think about this kind of problems.
That sounds very elegant, actually.
Last question, and could the next speaker please come?
Thanks, Arie. I was wondering, the invariants that you are able to infer, can you also infer quantified invariants with quantifiers, like universal and existential quantifiers?
I mean, only by reducing that to the quantifier for reduction, right? Like that sometimes you can reduce, for example, you say I have an invariant over a free variable, only in that way. So like to answer you then, no.